this is chapter 22, second to last chapter, cosmetics and personal care. Now, I really should have started this sooner, but I'm going to get a little bit more serious about citations. So I'll start off this chapter by saying this is APA style citation here. All images, diagrams, and information comes from the Extraordinary Chemistry of Ordinary Things unless otherwise mentioned and otherwise cited in the paper. So while there will not be any exciting demo today, we will learn a lot about everyday products, some of which we might already know a little about. Take the 2001 film Legally Blonde. The movie's legal reveal hinges upon the chemistry of a perm, or permanent wave. The killer is trying to pin the murder on her mother-in-law, that's about the same age as her, claiming that the murder happened while the daughter was showering, the murder of the husband. But she wouldn't have been showering after receiving a perm without risking the deactivating of the ammonium thioglycolate, which was mispronounced, of course, as well. Now, spoilers, while this isn't quite right, let's not let the facts get in the way of a story. I won't say good story, but a story. But depending on your source, people will claim that anything from no water at all for 50 hours is what you want, or no shampoo and soap is good enough. But or to even no, it shouldn't really have much of an effect. Maybe your perm won't stay nearly as long, but it shouldn't completely go away if you get it wet. Well, this chapter will look at these facts and the facts of how we treat our body when it comes to the bathroom. We've been using a wide variety of compounds to pretty ourselves since ancient times, sometimes at incredible self-risk. We've already mentioned we haven't really mentioned Botox much, but we've mentioned botulism toxin, which is, as you'll learn a little bit later, the key compound in Botox, which we did talk about botulism in the hazard chapter. But we've been known to use a variety of different plant products and heavy metals to pretty ourselves from times like ancient Egypt all over to just rather recently, honestly. Henna hair dye is a plant product that is still in use today in Africa, India, and the Middle East. Way to dye your hair. There's references to the Bible that refers to the Jezebels painting their eyes in 2 Kings. There are other such eye painting mentioned in Ezekiel. Such things as lead powders and arsenic wafers have been used to give the body a white pallor. Nightshade has been used in eye drops, especially in Italy. It used to be called belladonna. It was used to dilate the pupils and give you that large, doughy-eyed effect. More recently, 1915, radium was used in skin products under the false advertisement that the radioactivity would remove wrinkles. Cosmetics and all that's from the Quack Doctor. But cosmetics are a universal term to describe all these substances, meaning cosmetics, a substance that applied directly to the human body to make it appear more attractive. It comes from the Greek cosmos, which means order, it means adornment, and it can also mean the universe. We've seen the cosmos. Coming from the idea of Greek philosophy that there is beauty within order, and the universe itself, being very ordered, is thus very beautiful. Well, according to the Food and Drug and Cosmetic Act, however, cosmetics are technically considered anything that is applied to the body for cleansing, beautifying, and promoting attractiveness or altering appearance. So, according to them, soap isn't legally a cosmetic, but we're going to use it as a cosmetic, a generic term for cosmetics. We will differentiate medicines and cosmetics. Medicines we'll talk more about next chapter. And that medicines are often confused, but we'll define medicines as those that treat disease and illness and injury, while cosmetics just used to promote attractiveness. In the US, cosmetics from the following four categories account for about half of all personal consumer sales. Hair care products, perfumes and colognes, skincare products and emollients, and hand, face, and body soap. The material cost accounts for about 1/10 of the price of these things, but the remainder is all about packaging, advertising, research, labor, and of course, profit. So, don't cost a lot to make, but they cost a lot to make you want to buy them. In terms of chemical makeup, water is probably the most abundant compound in there. But after that comes the synthetic detergent. And that's present in a lot of different things, whether this is in shampoo or soap or toothpaste, all these guys have some sort of synthetic detergent. And of course, another key component is the fragrance, making it smell nice. Despite being less than 1% of the total weight, the fragrance usually makes up 25% of the raw material cost. So it costs a lot despite how little is used. Now, while the surfactant in soap and toothbrush and shampoo may be the same, they are not exactly interchangeable. The surfactant we use in shampoo may not, you don't want to be using that on your teeth. They're specially formulated to do more than just clean dirt, even though surfactants, as we talked about in the previous chapter, do clean dirt. The cosmetics need to be specially formulated with a mix of chemicals to achieve at least 3 kinds of tasks. That there's the principal function, one such as the cleaning function, which could be very similar from cleaning product to cleaning product. The second function usually relates to the cosmetic specific activities, such as toothbrush should probably freshen breath, or shampoo should provide body to the hair or luster to the hair, or soap should kill bacteria. And finally, there's the very subtle qualities such as convenience of use or odor or color or sometimes the general appearance in order to keep something competitive. You don't want to be using, as they say, they don't want to be using toothpaste that smells like garlic or anything, or a shampoo that looks like garlic. You want it to look good, flow nicely, and be like attractive and something that you want to use. Now, one of the most common ingredients of these cosmetics is the anionic surfactant you see there. It's based on the lauryl sulfate compound. So you take lauryl alcohol. Lauryl is the common name for that chain length of alcohol, and you react it with chloral sulfate. And what happens is you form HCl and the lauryl sulfate molecule. Now, by deprotonating it with a base, you can make various ionic compounds. Like you could have sodium lauryl sulfate, you could have ammonium lauryl sulfate, you could have triethyl ammonium sulfate. All these have slightly different properties, and so will be used in different ways. For example, sodium lauryl sulfate is insoluble in cold water. While this isn't a bad thing in toothpaste, it could be a little disconcerting in shampoo if you wash cold water and then suddenly you get a lot of solid crystals in there that for cleaning. But in the toothpaste itself, it's not a big deal because you're using kind of abrasives anyways. Instead, they use like ammonium or triethyl ammonium sulfate, which has a greater solubility, along with it doesn't dry out your hair as much. So by using those, it stays soluble, and so you don't have solid chunks in your shampoo, and so your hair can stay more moist. So we'll start almost immediately by talking about hair in general. Now, hair is composed of a protein called keratin. Keratin are in all types of hair. They're in nails and claws and horns and hoofs and feathers. All these contain keratin. But keratin contains a combination of 20 some odd amino acids. But one of the main amino acids is cysteine, which accounts for about 14 to 18% of the amino acid. As we'll see, cysteine has a methylthiol functional group. Amino acids usually differ by the functional group that's attached to the amine and the acid part. That, as we can see on the left, we have the methyl sulfur, which is part of the thiol group. And this methylthiol can make sulfur-sulfur disulfide bonds between other keratin strands. And this adds to strength of these strands of keratin. This disulfide bond is something we're going to talk about a lot. This is the same type of thing we saw with rubber. Rubber made those disulfide bonds upon vulcanization that made it strong even at high temperatures. So each strand will grow out of the living root that is embedded in a follicle, which is a microscopic sac under the surface of the skin that holds the root of the strand of hair. Now, each strand of hair in the scalp will grow outward at about a centimeter a month. And after 4 to 6 years, the strand will typically fall out to be replaced by a new one. So that's going to begin this whole process again. Now, each strand consists of, as we'll see here, a cortex, which is the central core of the strand of hair. It's the bulk of the strand, and it's responsible for the pigment. And it's surrounded by the cuticle, which is the scaly sheath that covers the cortex, that protects the hair. Now, the nearby sebaceous gland is the gland near the skin that's going to secrete an oily substance known as sebum. This is going to lubricate the cuticle and give it its gloss. It's going to prevent this guy from drying out. So it's going to keep the hair oily and glossy, and it's also going to generate some of the dirt, the greasy and dirty. If you have greasy and slime and oily hair, it's because you produce a lot of sebum. Now, yeah, as I said, too much sebum makes that. Too little would make your hair dull and dry and very wild. So you want a good management of those two things. Now, shampoo, while it should remove the excess dirt and sebum that's in the hair, we don't want to remove all of the hair's oil. Then it'll dry out. So the purpose of many conditioners in shampoo is actually to put some of the oil back in, put some lubricants back in to keep the hair lustrous and have some body, so that it doesn't just dry out and be all crazy. Now, other ingredients in the shampoo are there to stabilize the foam, act as preservatives, give the shampoo the proper viscosity, which is the ability to pour and flow. So if it was too chunky to come out, you're not going to be able to come out easily. Adjust its body. Some of it's going to adjust the pH of the shampoo, which is the acidity factor. Some of them are going to chelate any metal ions in the water, in the hard water, that would degrade the surfactants. And of course, and its cleaning power. And some of it's going to add color and fragrance, so it's nice smelling. Now, why is the pH important? The pH is important because that controls kind of how the cuticles form up. Slightly acidic conditions, the cuticle will tighten up and they'll kind of adopt a tight form that's going to a tight uniform coating to the surface of the hair. And because of that tight coating, it will reflect light back in a coherent manner. Because coherent means they build upon each other. When they build upon each other, it gives the hair that little bit extra shininess because all the light's being reflected in one direction. Now, under basic conditions, the cuticle will swell up and fluff out, and so the cuticles will kind of point in all different directions. So light is reflected and scattered in all sorts of ways and make it kind of look dull. So here we have some common ingredients of a shampoo. That here we have, purified water, which is just the solvent. The surfactant, with is the trimethyl ethanol ammonium lauryl sulfate, mustaric acid to adjust the pH, oleal alcohol to add some oils back in, some fragrance, formaldehyde as a preservative to keep it stable, and just some other additives to add color. Now, the next thing we'd like to talk about hair is hair coloring agents. They've been used since ancient times. So whether with the molecule lawsum, as we saw in henna, or in powdered metals, until 2018, the hair dye Grecian Formula, which I wasn't really familiar with, but the Grecian Formula product used lead acetate to darken the hair. They now use bismuth citrate, but the dye formed a dark lead sulfide compound that causes the overall the darkening of the hair follicles, or the darkening of the cortex. So if your hair is graying out and you want to darken it back up, using Grecian Formula makes lead sulfide. So not the safest. So that's why they switched to bismuth. Now, the newer dyes, the organic chemical dyes, actually dye through reactions of complex synthetic chemicals devised typically within the last 100 years. Hair contains two basic pigments. Melanin is the class of compound that is in the skin and hair coloring, but looking up online, it's actually melanin is not quite it. The proper one is maybe eumelanin, which is responsible for, they have two types of brown pigment and a black pigment of eumelanin that's responsible for a lot of hair colors, and pheomelanin, which is a red brown or yellow brown pigment that's similar to eumelanin. And they're both present in hair and skin, and they're responsible for a lot of different colors. Different combinations makes different colors. If you have, for example, just types of, if you have the black form of eumelanin and no other type, you get a kind of a gray hair. But if you have the brown eumelanin and only brown eumelanin, you actually get blonde hair. When you mix the brown eumelanin with pheomelanin, you actually get ginger hair. And the absence of any of these is where you get the white hair. In fact, pheomelanin is also responsible for, I think, the pinkness of the lips and the nipples, among other things. But so hair coloring typically requires first a bleaching process where you add hydrogen peroxide to decolor the pigments you got. If you don't decolor them first, you're going to just get a darker shade than you already have because you're adding dye onto other dye. But if you bleach it first, trying to make it essentially white, then you can just cover it up with a new dye, and the new dye is all we'll see. Now, temporary dyes are too big to actually go into the cortex. Things like this down here. It's a giant molecule. It can't go through the cuticle, and so it doesn't hang around for long. It maybe binds to the cuticle, but after several washings, it is washed away without a problem. Now, heavier dyes, lighter dyes like these guys are moderately long-lasting dyes. They last through many washes, but they will fade. Well, these guys are small enough they can migrate through the cuticles into the cortex, and so they stick around for longer periods of time. However, because they can migrate in, they can also migrate back out. So they will fade over time. The only way to really get a permanent dye is to find some way to trap the molecules in the cortex. So the way they do that is by actually mixing two chemical intermediates together that can first migrate into the cortex of the hair follicle, and then they will do a reaction to form a larger molecule that cannot get back out. So you typically have a primary intermediate and a secondary intermediate, and when you mix them together and oxidize, you form new bonds that cannot get out again. So, however, some of these molecules are kind of dangerous. Whether they can just invoke an allergic reaction, some of these are even suspected carcinogens. Now, while most dyes are free of some of these dangers, some will simply mitigate these dangers by putting a warning label on the dye. Warning, this may cause cancer, just like you put a warning label on cigarettes. Warning, this may cause cancer. Like, if you're willing to use it, you can take the risk. We are not at fault for that. When the consumer decide how much they want this dye. The next topic is all about how hair keeps its actual shape. Now, the hair keeps its shape partially due to the disulfide bonds, these sulfur-sulfur bonds that happen within the keratin. But it's also thanks to salt bridges, which are our ionic bonds made by the acidic and basic components of various amino acids, so they can form ionic bonds between different strands, and some hydrogen bonding from various OH and NH fragments of our amino acids. All these things essentially strengthen the keratin molecule to keep it into like the straight or curly or kinky or springy or wavy. They're all responsible for these are the same things that are responsible for protein folding. One protein folds in certain ways because of how these interactions occur. Whether you have disulfide bonds linking them together, or you have these salt bridges that stabilize this fold. So salt bridges, as a quick reminder, are from the free acid-base functional groups. Hydrogen bonds are weak electrical attractions between hydrogen on a NH or an OH group and the electrons on another oxygen or nitrogen group. While the hydrogen bonds are actually weaker than the salt bridges, the sheer number of hydrogen bonds will give dry hair a lot of its strength. So why does wet hair lose its shape? Well, water will disrupt all those hydrogen bonds and salt bridges. The water kind of blocks it out, and so the strand kind of falls apart. What was holding it together kind of separates. And then allowing them, as the water is removed, as the hair dries, those bonds can realign into a new configuration and thus a new shape. So what was looked one way before can reform another way. Now, a longer lasting rearrangement is accomplished through the permanent wave kit, or the PERM. So what happens is the kit uses a waving lotion and a neutralizer. Most waving lotions are the slightly basic solutions of thioglycolic acid, or the ammonium salt of thioglycolic acid. So you see that right up here. The purpose of thioglycolic acid is it adds hydrogens back and splits the disulfide into the thiol group. From there, essentially what happens is you can reshape this. You can straighten a curly strand or curl a straight strand, and while the hair is not really held together. And once you have it in the proper shape, then you add the neutralizer, which basically cancels out all of the extra thioglycolic acid and starts to reform the disulfide bonds, thus allowing to strengthen the hair into its new shape. Now, this is usually a pretty dilute version of hydrogen bond of hydrogen peroxide, so it doesn't really necessarily bleach the hair, but it's helped to freeze it back into its shape. While some people claim they can not to get permed hair wet for up to 24 to 50 hours, if this holds any sort of truth, this would be because the neutralization is slow. So the hydrogen peroxide process is slow, and so you want to give the chance to reform the disulfide bonds. But it's not really deactivating the thioglycolic acid. You've already kind of done that when you've added the hydrogen peroxide. The water would essentially be deactivating the hydrogen peroxide. So we're going to now talk about our teeth. When it comes to our teeth, the foaming surfactant is actually one of the least important parts of cleaning agents in what's called a dentifrice. Dentifrice. I don't usually use that. I usually use toothpaste, but dentifrice is just a term for any toothpaste or gel or whatever that tooth cleaning agent. Now, some toothpastes don't even use that at all. The FDA doesn't even consider the surfactant a active ingredient. What a true toothpaste has is an effective abrasive. Tooth is coated with enamel that's there to help grind food and to protect the interior. This enamel is largely composed of the mineral called hydroxyapatite. You can see that down here, calcium 10, PO4 6, OH2. This mineral is susceptible to acids. So acids will dissolve this. You have a hydroxide, which gets neutralized by the acid. Phosphate is actually a weak base, so also accepted by the acid. So especially acids that are present in what's called plaque. Plaque is a thin layer of polysaccharide that sticks to the surface of teeth, will harbor bacteria. So bacteria that are naturally in the mouth will convert sugars that we eat in food to this plaque. And this plaque can then stick to the enamel and be a growing point for more bacteria. This plaque houses the bacteria that will then convert the plaque itself into a mild acid that will begin to corrode the enamel, remove the calcium, remove the phosphate. And once enough corrosion occurs, a cavity forms, allowing bacteria to reach the interior of the teeth, which is where you get the bad stuff. The key to a healthy tooth is removing the accumulated plaque via gentle abrasion. And then what's going to happen over time is this will result in remineralization. You have some calcium and phosphate in your spit, and so it will precipitate, really solidify back onto the teeth, as long as you remove the plaque and leave a clean surface for the crystals the solid to reform. Some common abrasives: calcium carbonate, calcium pyrophosphate, calcium dibasic calcium phosphate, hydrated aluminum oxide, hydrated aluminum oxide, or aluminum trihydroxide, aluminum hydroxide, essentially, magnesium carbonate, talc, titanium dioxide, or tricalcium phosphate. Fluoride ions, what they do, they help maintain strength of the teeth, usually added by tin fluoride, sodium fluoride, or sodium fluorophosphate. And now in toothpaste. And what they do, they seem to work by replacing one of the OH groups in the hydroxyapatite, the enamel, to make a harder mineral, which is called fluoroapatite, and which is more resistant to corrosion by acids and by suppressing the bacteria's ability to generate the acid. So can't generate as much acid, it's harder and less able to be corroded by the acid. So protecting teeth for a longer period of time. Now, while the surfactants don't prevent tooth decay, surfactants, the foaming action do help remove debris, and they do help give you that nice clean feeling upon brushing. So common toothpaste, water, glycerol, which is help to keep the toothpaste moist, calcium, dibasic calcium phosphate, an example of an abrasive, carrageenan, carbohydrate seaweed with thickening agent, stabilizer, fluorides, and other additives. So enamel hardener, sweeteners, and preservatives. So this one doesn't really have much of a surfactant. Talk about now for the main part, we'll talk a lot about the skin. About 1/4 of every dollar spent on cosmetics goes to skincare in one way or another. Whether this be a moisturizer, soap, some sort of antiperspirant, all this is gonna protect the skin itself. Now, skin itself plays a very important role in healthcare, as does any other organ. It's going to keep harmful stuff out, keep all of our organs in, help us regulate our body temperature, do all sorts of great things that we don't really think about. The skin is at least composed of 2 layers, the dermis and the epidermis. The dermis is the portion of the skin that contains all the nerves, the blood vessels, the sweat glands, the active portion of the hair follicles, and also supports the epidermis. It's essentially the bottommost layer. The epidermis is the upper layer of the skin that does all the growing and replacing of skin cells. That typically they contain several tiers of cells. The bottommost tier is the one that's constantly dividing and pushing upwards, pushing the old stuff upwards as it grows. As they move upward, the cells eventually start dying and they'll become what's called the stratum corneum, which is the outermost layer of skin, the protective shielding of 25 to 30 layers of dead cells, which is why you can get minor scratches on your skin without really hurting you. It's like you're cutting through the dead layers of skin. Otherwise, if you cut through the new layers, each time you got a scratch, you'd be hurting your living cells. But having a dead layer of skin cells protects you. Of course, that also leads to flaky skin, because you can peel the dead skin cells off. So now the water content in your skin controls its behavior. If you have too much water in your skin, it promotes fungi and bacterial growth. So if you've got very wet feet or wet body parts, you can get, the athlete's foot or jock itch, where you can essentially grow bacteria that they thrive on the water, grow fungus that thrive on the water. Too little moisture, and you get flaking and cracking. So ideally, you want about 10% water mixed in there. The body will do its best to try to protect the skin by producing its own sebum, which will prevent water evaporation. So you're kind of coating the skin with a thin little layer of oil that prevents it from drying out. But this sebum is only really produced where hair grows. So not the palms, not the soles of the feet, and there's several other places where you don't really expect body hair. But many of our lotions and creams that we put on serve as a similar purpose of the sebum, that either moisturizing our skin to keep the proper amount of water, or filling in the wrinkles, if the case may be. But another thing your skin does is control its body temperature through perspiration. Perspiring is from the Latin to breathe through. It helps your body breathe through the skin. Your sweat glands cool you off through producing sweat out of the eccrine glands, which cover all your skin, secrete a slightly acidic dilute solution of KCl and potassium chloride and sodium chloride. They produce some lactic acid and some urea and some glucose. When the sweat evaporates, the body is cooled, and this sweat typically has no odor. So basically, it takes energy for sweat to leave, to evaporate. Well, it's going to absorb the energy from the body. So as the sweat leaves, it's absorbed energy from the body. So your body has to get cooler because the sweat is lost. Now, the apocrine glands, which are located under the arms, in the groin, and several other places, do produce a different type of sweat. They secrete still an odorless fluid into the hair follicles there, but oftentimes bacteria in those places can convert that into essentially the stinky thing known as BO. So the apocrine glands don't always smell, but having bacteria there is what causes them to smell. So we use antiperspirants and deodorants to fight that. So the antiperspirants themselves, things like aluminum, like tetrahydroxide chloride, or basically different types of aluminums typically, will cut off sweat glands for as long as up to several weeks, and as well as killing the bacteria. Antiperspirants essentially prevent you from sweating by blocking up your glands. So it keeps you from sweating. Of course, that can be dangerous to some extent because then your body can't release sweat if it's really hot. So it can't cool down the body if it's very hot. So antiperspirants not always the safest. Deodorants just try to cover up the odor and kill the bacteria, either with things like zinc salts or antibiotics. However, daily washing usually can solve many of the problems. So washing off and trying to kill the bacteria other ways. But deodorants are maybe slightly safer. Now, so we've talked about a series of cleaning products. What about just other various beautification products? Products such as lipsticks. Lipsticks provide a softening and protecting film to the lips, in addition to adding color. About half of the weight of the tube is actually castor oil. Castor oil is a mixture of a triglyceride derived from plant seeds, which serves to both dissolve the dye and to make it flow easily when warmed by the body heat. So the tube can keep its shape, and then when you press it against the lips, it melts into essentially a liquid that coats the lips. Most of the remainder of the tube is just a mixture of oils and waxes, hydrocarbons, esters, lanolin, and polymers, all to help give you the desired texture, the desired melting point, and the flow rate to keep the lips moist and soft. We want to flow on, but hang around there. The remaining materials, the dyes, the perfumes, and the preservatives make up a very, very small percentage of those. Another thing commonly used, eyeshadows. They often used intensely colored inorganic dyes incorporated into beeswax, lanolin, and other hydrocarbons. Things like ultramarine blue is a polymer of aluminum, oxygen, silicon, sodium, and sulfur. Some of the dyes are iron oxide complexes. Some are even just carbon black, so black carbon. Some are titanium oxide for a white powder that essentially you're just adding them on to help you're painting your face with some dyes in order to make it stand out. Now, mascara is actually only simply a dye for your eyelashes. As your eyelashes typically fade and are pale on the ends, you can't see the eyelashes' true length. But by dyeing and darkening the ends with these natural dyes and inorganic pigments or carbon black, they become more visible and thus appear at their true length. So it doesn't actually lengthen your eyelashes. It just makes them appear their full length, so they're longer and more beautiful. Things like nail polish. Nail polish are actually a specialized flexible lacquer that needs to bend with the nail. So pigments, the same type we might see in eyeshadow, gets mixed together with nitrocellulose, plasticizers, and resins, and they're dissolved into a hydrocarbon and ester solvent. So it's essentially we make a plastic that's mixed with dye and it's dissolved. So when you paint your nails with this, eventually the solvents will evaporate. And when they evaporate, they leave behind the polymer film that thus grips to the nail. A nail polish remover often contains either ethyl acetate or acetone that essentially sometimes the similar solvent that was used to put it there in the first place. But they sometimes also contain castor oil because or lanolin and other types of oils because these solvents will remove the oil, the sebum in the skin, and leave your nails dry and brittle. So you want some oils to leave behind to keep some oil on the nail. Face powders try to dull the shine that's created by sebum and perspiration while adding a slight tint, a texture, or odor without trying to call attention to themselves. Like an example, some face powder might contain talc, kaolin to absorb the water from the sweat. Zinc oxide is a hiding powder to kind of hide some of the imperfections. Magnesium stearate to provide texture, as well as zinc stearate. Mineral oil is a emollient, so I think it's some sort of moisturizer. And some cetyl alcohol and lanolin as a binding agent, softening. And then you have like coloring agents and perfumes, which brings us eventually to perfume itself. Perfume is another type of ancient cosmetic that we've since improved upon. Perfume is from the Latin through smoke, that might be referring to smoke of incense used in ancient ceremonies or the smoke of odorous plants used. A perfume is typically a blend of various synthetic chemicals, animal oils, and extracts of fragrant plants, all dissolved in about 10 to 25% solutions of alcohol. All that's to help volatilize them, to get it into the gas phase so it can smell up the place and so you can get those beautiful odors. Cologne is just typically a much more dilute and much less expensive version of perfume. It's short for eau de cologne or water of a cologne, which refers to Cologne, Germany, where an Italian Giovanni Maria Farina settled in 1709 and began manufacturing a lotion based on citrus fruit. Either way, modern perfumes and colognes are a complex combination of over 4,000 natural plant and animal products and over 2,000 synthetic chemicals blended together to achieve the three phases of a perfume. Phase one is the top note, which is the phase that vaporizes most quickly and thus reaches your nose. The first thing, it's the first impression you get. A lady enters a room wearing perfume. What you smell first is the top note. It's the first thing you're going to notice because when it gets to the gas phase, it can spread more quickly and reach your nose more quickly. The middle note is the most noticeable odor. It's the thing that's going to hang around for a long period of time, but it's going to come. It's the overwhelming odor you're going to notice. And then finally, the end note is the residual, long-lasting note. It's a fragrance that will linger. While everything else has escaped to the gas phase, that's going to hang around to the very end. We've since improved on the way we make perfumes. While some natural products used to be cruelly harvested from animals, such as civetone from the Ethiopian civet cats, where they produce this odor in the glands, and they had to scrape the glands of the cats to get this chemical, we can now synthesize this without the animal cruelty. So it's possible to get beautiful smells without the cruelty. But we see some of the compounds over on the right, like some citrus smells. There's some like rose and lavender and pine needles and all sorts of smells. You combine them together for what you want. Do you want to smell like the beach? You can find the right combination to give you that, invoke that idea of the beach. Now, the last cosmetic, while being the most natural cosmetic, is actually maybe perhaps one of the most dangerous. We're talking about tanning or sunlight. Before we talk about this, we need to talk about how the body reacts to light, and we need to understand how light itself works. So, light is a form of energy from the sun that we call electromagnetic radiation. This EM radiation can also be in the form of X rays, microwaves, ultraviolet light, infrared light, even TV and radio waves are considered electromagnetic radiation. So, we produce it at home just the same as the sun produces it. When understanding this energy, we think about it as undulating as a wave at a fixed or nearly fixed velocity of 3 times 10 to the 8th meters per second, also known as the speed of light. These waves are spaced at set distances apart, called the wavelength. So the distance from wave to wave, crest to crest, or valley to valley is our wavelength. As they move at their speed of 3 times 10 to the 8th, the repetitions of these waves can be measured as a frequency, which is the number of waves that will pass a fixed point given a specific period of time. So we can measure the wavelength and the frequency of some sort of electromagnetic radiation. Well, these two measurements are reciprocals of themselves. So the fewer the waves you have, the longer the wavelength. They'll travel through the point. So like a long wave, you would get less waves traveling through a point. The shorter the waves, the more waves you would see traveling through a point. Now, these are indirectly related to each other based on the speed of light. Now, these waves will have varying energies, which is directly tied to its frequency. So high frequency or shorter wavelengths will have higher energy. X-rays are an example of a high frequency electromagnetic radiation, and so they are more damaging. Radio waves are low frequency, long wavelength, and thus we consider them safe. We have been spraying them around the world for decades with essentially very low harm. Well, all visible light falls into a very small region of 700 to 400 nanometers, where it's capped on the left above 700 with infrared, and capped on the right below at ultraviolet. Another way to say nanometers, so say 4 times 10 to the negative 7th meters to 7 times 10 to the negative 7th meters. All this is the Roy G. Biv spectra, the red, orange, yellow, green, blue, indigo, violet, putting those in the proper wavelengths order. So infrared is the invisible heat-carrying light. Ultraviolet is the invisible rays of the sun that do all the nasty damage that we hear about. So ultraviolet, as we're going to see, is going to be broken into 3 different types. But some are absorbed by the ozone layer, much of it penetrates through. And a suntan is our body's way of protecting us from some of these harmful UV rays. Any exposed skin will absorb these rays, and so the body produces melanin to help screen out and absorb this light by converting it into harmless heat. So it absorbs it into the outer layer of skin and produces heat instead of allowing it to fully penetrate through and damage the dermis and the lower epidermis. Now, the potential damage comes from the various ranges of UV-vis light. The book only talks about A and B, but I'm also going to mention C. UVC ranges 100 to 290 nanometers. This is the most damaging light. Almost all of this is absorbed by the ozone and atmosphere. We often use UVC as a disinfectant radiation. So on both water and hard surfaces, if you shine UV light on a water source, you're killing the bacteria in that water source. You shine it on a area that's infected, you're killing any bacteria on the surface because the light damages the DNA and thus killing the bacteria the same way as it damages our DNA. Now, UVB is from 290 to about 320 nanometers. It's still partially absorbed by the ozone layer, but enough of it does reach the surface to be considered harmful. While UVB exposure leads to the production of vitamin D in the body, very little exposure is needed to get the proper amounts of vitamin D. Like 5 to 15 minutes is enough to keep the vitamin D level high. So it also causes, the big problem is it also causes a very short-term and long-term damage to the skin. The acute injury, the short-term, is sunburn, the redness, the blistering, the peeling of the skin. It's the same type of damage that's caused by ionizing nuclear radiation and or intense heat. So you get horribly burned, you get the same damage as sunburn. You get hit by radiation from you stand too close to a reactor, you get the same type of damage as a sunburn. It's just the degree. It kills the cells. The UVB causes direct DNA damage. So it damages the DNA in the cells. When the cells in the epidermis are irreversibly damaged, they undergo what's called a controlled cell death. And the sunburn is actually inflammation response to this cell death. You try to remove and replace the dead skin cells, which is why your skin often peels after a sunburn. You're peeling off the now dead skin. So the body has to kind of push them out and replace them with the new one. And the red is also trying to help block out the sun. Long-term exposure, on the other hand, will lead to skin cancer. How that works is that some of the cells damaged by the light, they get damage to the DNA, but not enough to create cell death. And if this occurs, it will eventually produce just the right conditions for uncontrollable cell growth. So you damage one part of the DNA and the molecule doesn't notice and it doesn't screw up anything too big. Then it keeps passing on that goof up throughout all of its cell line. And then some more gets damaged and that doesn't get caught. And eventually you get to the point where they accidentally removed all the limiters on cell growth and you have skin cancer. In addition to this, UV light causes wrinkles due to the destruction of the protein collagen in your skin. So now people with excess melanin are largely protected from many of these effects because they can absorb that light and harmlessly transfer it into energy. So it's not less likely to penetrate into the epidermis and dermis and damage the skin. And it's also less likely to destroy the collagen because, as I said, if it's absorbed in the stratum corneum, it's not going to make it in and damage the skin where that can't be replaced. Now, UVA is 320 to 400 nanometers, will fully penetrate all of the ozone layer. Now, while this does provide a slow tan and is far less dangerous than UV B or C, it is not necessarily harmless. It's thought that it still might cause some DNA damage, maybe not as much, maybe through different mechanisms. But skin tan, your body is responding by producing melanin as it absorbs the light, like, oh, we need to block some more melanin, so it produces that. And it's a slow process, so UVA does the thing. Well, what does sunscreen actually do? Sunscreen provides varied protection by blocking out various wavelengths of light. Some only block UVB and C. Others will block the full range of spectrum. But the most effective ones are things like inorganic oxides, like zinc oxide or titanium oxide, that causes scattering of light. So all types of radiation bounce off harmlessly, letting none of it through. But there are some that are very selective in absorption. That we use modified benzene and ketone rings, such as PABA, the para-amino benzoic acid down there, that absorb lights at certain frequencies because of the benzene rings. And that causes to block out some wavelengths, but not others. Well, the sunscreen protection factor is one thing that's often reported, and that is the fraction of ultraviolet radiation that a sunscreen or suntan lotion will allow to pass through to the skin. So, SPF tells you by what factor the UV light is absorbed. SPF 6 would mean it only lets 1/6 of all the sunlight through. So, a person without sunscreen stays out for 1 hour. SPF 6 would allow that same person to stay out for 6 hours and get the same amount of sunlight. SPF 15 would block out all but 1/15. So it's essentially blocks out almost all UV radiation. You'd have to be out almost all day for that to work. Now, to minimize risk for people with lighter skin, it suggests they use SPF 10 to 15 until a tan starts to develop. And then you can start dropping the SPF a little bit. But you want at least a small base tan before you try to increase the amount of sunlight. And when you put on sunscreen, they tell you to work it in 30 minutes before going out in the sun, because it takes a while to work its way into your outer layers of skin and stick. You don't want to immediately sweat it off. If it hasn't worked its way into your skin, it's not going to hang around for any period of time. Now, one last thing is sunless tanning lotion, like dihydroxyacetone down there. All these other molecules are types of sunscreens, but down here is dihydroxyacetone, which is our sunless tanning. What that does is it reacts with the amino acids in your skin to produce a brown pigment. While this browning may look like melanin, it is not the same as natural melanin. It does not protect nearly as well as a real thing. It should be used with caution, especially if utilized with natural tanning methods. So don't just slap this on yourself, look like you're nice and tan, and then go out in the sun. It's not going to work quite like that. It blocks some, but not as good as the real stuff. Once again, we hit a very relevant chapter for our everyday lives. This chapter, hopefully you're all in a personal health class. Hopefully you know how to properly bathe, shower, wash your hair, put on cosmetics, put on makeup. But now hopefully we know a little bit more about what goes into this. What makes a perfume smell like it does? What does suntan lotion actually do? I mean, all this, the science of beauty is a highly complex thing. We've been constantly, once again, science and technology fighting against each other. Back in the day, we used lead-based powders to help give women pale skin. We used various toxins to help redden the cheeks or redden the lips. In fact, they used to pinch the cheeks to try to burst the blood vessels in the cheeks to give that rosy cheeked look. I mean, the damage that we do to our bodies to try to look better is a very complex situation. That, yeah, we need some sunlight. Vitamin D is important for our growth in our body. But do we need to go out and tan? Not really. I mean, we want to try to reduce wrinkles to get that healthy look, but things like Botox can deaden the nerves. And so you're essentially immunizing your body to toxin, and so you need more and more of it to get the same effect when it wears off. So we're constantly fighting against this and trying to make safer and healthier things that won't irritate the skin, irritate the eyes, chemicals that are less toxic for the environment, less harmful to the source of them. But it's a never-ending battle. It's a never-ending battle. But one more chapter, one more thing to think about, and one more test.